Lesson 2 is going to be a description of Newton's laws, specifically his first and second law. This first page of notes in Lesson 2 is going to deal primarily with Newton's first law. However, I have to give you kind of a sneak peek to what the second law is, and that's what I have up here in blue to facilitate our discussion of Newton's first law. So the sneak peek I'm giving you is Newton's second law is just an equation, F equals ma, and now there's more of a description and analysis to it, which we're going to do after this, part 1 of Lesson 2, the law of inertia, that I'll begin in a moment. But we need to understand that the relationship between forces and acceleration is explicit, and it says that if there is a net force, there is an acceleration, because as a vector equality, they will go together. So the acceleration and the net force will act together. The F in F equals ma, even though textbooks typically don't put F net into their notation, is the force net, and then the mathematical, more explicit notation is that F net is the sum of all the competing forces to give you the net effect. Okay. Back to Newton's first law now. Well, Newton's first law is that famous statement, objects at rest remain at rest. Well, there's a little more to it than that. That is correct, that objects at rest, Newton said, will continue to want to stay in their state of rest. That is natural. That is what nature would want. However, the equivalent and absolutely valid state for nature to be in is that objects with constant velocity will remain in states of constant velocity unless acted on by a net. And you can see I have net here in big bold letters. I'm going to keep emphasizing that. It has to be a net force. Just like we saw the monkey pushing on the car, that doesn't necessarily do it. That doesn't necessarily move the car. You need a net force to get the car to move. You need those competing forces to have a winner. All right. Well, this was a big deal in terms of a realization of how the world works relative to what nature presents us. And Newton was the first one to see this. So here I have, just again emphasizing the notational difference that net force is sometimes written as sum of the forces. So I'll just get that again quickly in here. So that's the same thing. Sum of the forces, net force. So what Newton showed us in the second law is that if there is no net force, then the acceleration is 0. And if the acceleration is 0, there cannot be a net force. Well, this took us out of the Aristotelian, Aristotelian's a fancy word for what Aristotle taught us, belief that nature naturally wants objects to be at rest, because down here on Earth, where all of we mortals reside, there's friction in our everyday lives. So if an object is at rest, it wants to stay at rest. So what I have here is the notes are already annotated in, but to give you an idea of the conversation that goes with it, at first, we're only looking at the box that is at rest, right? And it wants to stay at rest. Right? If the wind doesn't come along to blow it in one direction, if we don't push it in one direction, nature wants objects at rest to remain at rest. Well, what Aristotle also saw is that when you flick an object and you put it into motion, nature still wants it to be at rest, because what Aristotle saw was friction. And later, when we identify specific forces that we'll be using to problem solve, so I'm not going to go into great detail now other than to correctly say that that would be kinetic friction. Dragging it to a stop would bring it to a stop. So Aristotle, and again, all of us mere mortals, believed that that's the way the world works. Objects should be at rest. Well, Newton, being Newton and being brilliant, historically brilliant, if they're still talking about you some 300 years after your passing, then you were a pretty smart person during your lifetime, and that's what we're talking about with Newton. When Newton studied mechanics, he studied celestial mechanics, in other words, the motions of the planets. And what Newton realized was for the planets to remain in Kepler's orbits year after year, consistent as the seasons, year after year, that a natural state for those objects had to be in a frictionless environment. Nothing was bringing them to a stop. Nature didn't want to stop them. So it was every bit as natural to say objects in motion want to remain in motion, and specifically constant velocity motion, unless acted on by a net force. So what we're looking at here in terms of adding forces into the problem, and again, this is kind of a peek ahead because we'll do specific forces over the next couple pages of notes, is that if a box is sitting on the ground, you will have gravity and a gravitational force pulling down on it. The ground will be pushing back up on it, keeping it from sinking into the ground, and we're going to call that a normal force, and it'll be mathematically normal, meaning 90 degrees to surfaces. And if that's it, so forget about the left or right motion for a second. So if the box is just sitting on the ground, there is no net force because the normal force and gravity will cancel out in terms of competing forces on the box, and the box would just sit there. Well, what if we are going to flick that box to the right and give it some initial speed? Well, at first, let's go to a frictionless world. Let's pretend it's on a sheet of ice, and not only is it ice, it's the world's most perfect ice, and there is no friction. So that box would slide to the right forever upon Newton's realization that that's every bit as natural as just sitting there not moving. So with no net force in the x direction, it would continue with this velocity forever. Well, let's go back to the world we live in where there's friction. So friction, of course, is going to drag it to a stop. If an object is moving to the right, you have to pull on it to the left, so friction will exert a force, a pull to the left, bringing it to a stop. And we, of course, can also have applied forces in problems, and we will as we go through this unit. And what I have shown here is, what if we pulled on the box to the right? So just consider pulling on a box to the right with 10 newtons. If there's a pull on the box to the left with 10 newtons, whether it's friction or any force, there is no net force now in the x direction, and we again have the condition satisfied that the object would continue to move to the right if given an initial velocity. Now, another way of thinking of this is let's put the object back into motion with its velocity to the right and no x forces, so no force pull and no friction. So we just put it in motion to the right, and it's sliding happily along and would do so forever. Well, to maybe give you another way to think about it in terms of having forces act on it but not have a net force would be, let's say that it's moving to the right at that constant velocity, and part of our magical powers now is that we have the ability to instantaneously put that force of 10 to the right and instantaneously put this force of 10 to the left onto the box. So the box is sliding along and we snap our fingers and those two forces appear simultaneously. The box would continue to move as if the forces were not there. And I know, boom, that's not something that maybe you would have thought of, but that's the way the world works. It's all about this net force and understanding the motion. Well, I'm going to stop the first part of lesson 2, part 1 here, so you can annotate this. We're going to discuss Newton's first law in class together, and then we'll move on to a formal description of Newton's second law and F equals ma.